Hello everyone, today we are going to talk about a little known concept called exterior algebra. It includes bivectors, trivectors and several higher order vectors. This provides a very useful replacement for cross product. Vectors are geometrical objects which have direction and magnitude. For example, the vector u over here takes the point B to point A. It moves 5 units in x-axis and 2 units in y-axis. Similarly, the vector p over here also moves point E to point F by moving 5 units in x-axis and 2 units in y-axis. So we call these two vectors to be equal, right? The way you represent them is by saying it's 5 times E1 plus 2 times E2. In general, a vector can be represented as sum of A1 E1 plus A2 E2 etc. Or succinctly we just write sigma AI EI. Similarly, any vector b can be written as sigma pi ei. Let's define some operation on vectors. Let's start with vector addition. Adding two vectors gives a new vector. In this example, vector u is added with vector v. First, we construct a new vector v dash which is same as vector v except that v dash starts at the tail of u. And w is the net displacement from u to v. For example, the net movement is vector w, which is a sum of displacements in both x-axis and the y-axis. Mathematically, we can say that the corresponding scalar coordinates are being added. The next operation we define is dot products. The dot product of two vectors is a scalar. We define it as vector a dot vector b is equal to sigma ai bi. The third operation is the cross product. The cross product of two vectors is another vector. It is defined by a determinant. So vector A times vector B is given by the determinant E1 E2 E3, A1 E2 A3, B1 B2 B3. The fourth operation is a scalar triple product. Scalar triple product takes three vectors and gives a scalar quantity. It is defined as A dot B cross C. It's defined by the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. A problem with scalar triple product is it can be rearranged in non-trivial ways. For example, A dot B cross C is same as A cross B dot C, but it is also equal to minus B dot A cross C. Now we are ready to tackle our main topic, bivectors and more. It's a giant leap from cross products and scalar triple products, and it's way more intuitive, right? So why did we end up learning cross products in the first place? It's because Oliver Heaviside and Josiah Willard Gibbs developed vector calculus for physics, which used a lot of cross products. You might have heard of Green's theorem, Gauss's theorem and such. But even lot before this time, we had exterior algebra, which was developed by Hermann Grassmann. This is shortly after quaternions were developed by Hamilton. And this was extended to a beautiful system called the geometric algebra by Clifford. We also call it the Clifford algebra. We'll not talk about the Clifford algebra today. So what are bivectors? Bivectors are something that represents an area and a plane. Just like vectors, bivectors also have a magnitude and an orientation. But the magnitude in this case is an area and the orientation is the plane in which it lies on. Similarly, trivectors represent a volume and the orientation is the hyperplane which it lives on. Note that bivectors are not same as 2D vectors. No. Bivectors represent area in any dimension. Similarly, trivectors are not 3D vectors. They represent a volume in any dimension. Just like vectors, bivectors also have a sign. For example, positive sign means along the direction that we decided and negative means the reverse direction. Similarly, bivectors are either clockwise orientation or anti-clockwise orientation. And so on goes for higher order vectors. So just like two vectors, two bivectors are equal if they lie on the same plane and they have the same oriented signed area. For example, 3xy is 3xy. It doesn't have to be a parallelogram or a square or a sphere, doesn't matter, as long as it's the same area, they are the same. Similarly, you can also alternate the axis xy to yx, and the sign would change from 5 to -5. Just like in vectors, if you had taken in the positive x orientation or a negative x orientation, you could have flipped the magnitude from +3 to -3. For example, 3xy is 3xy. In other words, any object whose area is 3, whether it's square or a parallelogram or circle, if it lies on xy plane, they are both equal. Remember, the orientation need to be maintained. If xy is alternated to yx, then the sign should change to -5x. Right? So 5xy is equal to -5yx. This is just like in vectors. So if you take in the positive x, 3 plus x is same as -3 times -x axis. Now we are ready to formally define what's an exterior product. An exterior product of two vectors give a bivector, and bivector and vector gives a trivector. Bivector with a trivector gives us a 5-vector, etc. Right? So what's the exact law? First, it's associative. Essentially, we are saying the order matters in totality. It doesn't matter how you individually do them, as long as we don't permute things, they remain same. Right? That's the first property. The second property is distributive. It means that if you extend along any vector, the total area just increases. This multiplies by the same number. If you made b 2 times, then the area becomes 2 times. Right? And the last property is self-vanishing. For example, if you bring it close, the entire volume goes to 0. Right? This is because they represent the gap between the vectors. And if the same vector, there is no gap between them, hence they vanish. The most important consequence of the self-vanishing property is that it becomes anti-commutative. If you change the order, the sign changes. We already saw it with the xy plane. If xy becomes yx, the sign changes. Right? If u times v is equal to minus of v wedge u. We can prove it by applying the self-vanishing property on a plus b wedge a plus b. On expanding, we get a wedge a wedge b wedge a, and b wedge b equal to 0. Of course, a wedge a and b wedge b are zeros, so the only thing that remains is a wedge b and b wedge a. In other words, a wedge b is minus of b wedge a. Okay, the first example is two-dimensional vectors. And you can expand it just like a normal algebra. And the only thing you have to remember is even vanishes, e2 vanishes. And the other thing is e2 even is same as minus even e2. So you would end up with a single scalar multiplied with even e2. In general, it will be the determinant of a1 a2 b1 b2 multiplied by even e2. A more advanced example is two three-dimensional vectors. This time I have eliminated the vanishing terms so that you don't waste time multiplying them. And the only thing you have to remember is permuting it back. For example, e2 even is minus even e2, so 21 minus 10 gives 11, right? As a special case, if you assume e1, e2, e3 are orthonormal unit vectors, you can know the actual volume by the Pythagoras theorem. Remember that a wedge b here still gives a bivector. It represents an area in some unknown plane. You could ask what this 11 minus 24 minus 62 mean. You can imagine shining a light to that plane and see how much shadow it casts on the individual e1, e2, e1, e3, e2, e3 planes, and you would know the orientation is either 11, minus 24, minus 62. The minus 24 means the shadow is cast under the plane instead of over the plane. Okay? So now we are ready to graduate to trivectors. Remember, in the first example, we had only e1, e2. There is only one 2D plane in 2D. Similarly, there is only one 3D hyperplane in 3D whose components are even e2, e3. Why? Because every other combination vanishes. For example, even, e3, you can apply the associative law and say even vanishes to 0, so the whole thing vanishes. So all of them must be distinct. We'll take a first example. This is 3 vectors. So we have to compute A wedge, B wedge, C. A wedge B we have already done in the previous example 3. So we'll take it, it's a bivector. Now we are multiplying that bivector with a normal vector to get a trivector. You will also get 3 terms, but now you have to permute multiple times. Even e3, e2 is permuted once to get even e2, e3, hence the negative sign. e2, e3 even has to be permuted twice. 3 and 1 gets permuted to say e2, 1, 3. Next permutation substitutes 1 and 2 to get 1, 2, 3. So 2 swabs makes the sign cancellations go away and you get minus again. Adding all of this up, you get minus 123 even e2, e3. In general, the trivector produced by the wedge A wedge, B wedge, C when they are 3 3D vectors is a determinant, because all the even permutations the sign cancellations go off and all the odd permutations there's a sign change, which is what we call determinant. Now we see how many degrees of freedom a k vector has in n dimensions. So you have n axis dimensions to choose from and you have to pick k of them. So it is cnk, which means a vector in 1 dimension or a bivector in 2 dimensions or a trivector in 3 dimension or a 4 vector in 4 dimension, etc. all have exactly 1 degree of freedom. And we call these the pseudo scalars because they behave exactly like scalars. Similarly, a vector in 2 dimensions or a bivector in 3 dimensions or a trivector in 4 dimensions all behave like a vector. They have the same degree of freedom as the dimension itself. So we call these pseudo vectors. In other words, all the pseudo scalars require only one number to represent them. For example, a bivector in 2D requires just one number, a trivector in 3D requires only one number. In other words, they behave exactly like scalars. Similarly, a bivector in 3D requires only 3 numbers to represent. In other words, a bivector in 3D can be represented as a vector. Similarly, a trivector in 4D requires only 4 numbers, which means it can be represented as a vector in 4D. That's why we are calling it pseudo scalars and pseudo vectors. Now if you remember the cross product has the exact same definition as our bivector in 3D. Why? Why did it work? Because bivector is a pseudo vector in 3D. Now you can immediately see why we could not have come up with a cross product in 4D, because a bivector in 4D requires 6 parameters to represent. Hence, cross product of 2 4D vectors would end up having to be a 6D vector, which is not convenient. Instead, we use a bivector. And even in 2D, cross product of 2 vectors actually is a scalar. If you are done, you would only see there's a k, there's a single number for 2D because there's only one plane. Similarly, triple products are represented by trivectors. Now the scalar triple product in 3 dimensions is represented as a scalar because it needs only 1 degree of freedom, right? So it acts exactly like a scalar. Now why does it have all the properties of that we discussed, like if you change the order, sign changes? Because it's a trivector. We are told there is this anti-commutative law, so we can permute as much as we want. We can keep moving things around, and every time we swap, a negative sign comes in, right? So all the properties of scalar triple products trivial if you think of them as trivectors or exterior algebra. Now notice that there cannot be a scalar triple product in 4 dimensions because that would be a 4D vector, right? But there is something else that is analogous. So there is an operator that you can define on 4 dimensions which takes 4 vectors to give another 4 number. Sorry, you can take 3 vectors and give another number. So trivector in 4D is a pseudo vector. But in general, the only reason the cross product and scalar triple products worked were because they were pseudo vectors and pseudo scalars, and that's also the reason why they simply break down in higher dimensions. But our bivectors and trivectors extend well beyond 3D. They work beautifully, and all the formulas of scalar triple products actually make sense. And you don't have to remember all these formulas to compute a scalar triple product. You don't need to remember the complicated formulas to do a cross product. It is just multiply. Thank you everyone. I hope you enjoyed the talk on bivectors and the exterior algebra.